Today we are diving into one of the most important building blocks in modern system design, distributed caching. Systems like Redis and Memcached help applications serve millions of requests while keeping response times incredibly fast. In this video, we'll understand why caches exist, how they work, how they scale, and the techniques companies use to build reliable distributed cache systems. Imagine Amazon's product page suddenly goes viral. Millions of users are requesting the same information. Without a cache, every request goes straight to the database. CPU usage climbs, disk activity increases, and response times start getting slower. The problem is simple. We are repeatedly fetching the same data. Instead of querying the same database every time, we can keep frequently accessed data in memory, much closer to the application. Every cache request has only two outcomes, a hit or a miss. A cache hit means the data is already in memory, so the response comes back almost instantly. A cache miss means the application has to fetch the data from the database, store it in the cache, and then return it. The goal of every caching system is straightforward: maximize hits and minimize misses. Before deciding the architecture, let's define what we want. We need a sub-millisecond reads, an in-memory key value store, horizontal scalability, replication for reliability, and an eviction strategy when memory becomes full. These requirements will guide the rest of our design. Memory isn't unlimited, so eventually the cache fills up. At that point, something has to be removed. LRU removes the least recently used item and is a solid default. LFU removes the least frequently accessed item, making it useful when long-term popularity matters. FIFO simply removes the oldest entry, while TTL automatically expires data after a fixed amount of time. The best choice depends on your workload. Whenever data changes, the cache and the database need to stay in sync. Write through updates both immediately, giving strong consistency, but slower writes. Write back writes to the cache first and updates the database later, making writes much faster, but introducing some risk if the cache fails. Write around skips the cache completely and writes directly to the database, avoiding unnecessary cache updates but causing the next read to miss. Reads are usually handled using cache aside. The application checks the cache first. On a miss, it reads the database and stores the result back into the cache. Another option is read through, where the cache itself fetches missing data. Cache aside is by far the most common approach you'll see in production and interviews. Eventually, one cache server isn't enough. To increase capacity and throughput, we split the data across multiple servers using sharding. Instead of storing every key everywhere, each server owns only a portion of the key space. Adding more nodes increases both storage and performance. Scaling improves capacity, but it does not protect against failures. That's why each shard is replicated. A primary node handles writes, while one or more replicas keep copies of the data. If the primary fails, a replica can quickly take over, allowing the system to continue serving requests with minimal interruption. Now comes one of the most important concepts in distributed caching. A simple approach like #key %n or number of servers works until you add more or remove a server. Suddenly, almost every key maps somewhere else, causing a massive wave of cache misses. Consistent hashing solves this by placing both servers and keys on a hash ring. When the cluster changes, only a small portion of the keys move, making scaling much more efficient. Consistent hashing solves one problem, but there's another. With only a few physical servers, data may not be distributed evenly. Some servers end up storing far more data than others. Virtual nodes fix this by placing each physical server on the hash ring multiple times. This spreads keys more evenly, balances the load, and makes scaling much smoother. Let's briefly look inside an LRU cache. Two data structures make it work. A hash map provides constant time lookups, while a doubly linked list keeps track of which items were used most recently. Every access moves an item to the front of the list, and when the cache becomes full, the item at the end is removed. Together, they make reads, writes, and evictions all run in constant time. Let's recap. Caches speed up applications by storing frequently accessed data in memory. Eviction policies manage limited space. Read and write patterns control how data moves between cache and database. Sharding provides scalability, replication provides availability. Consistent hashing minimizes data movement, and virtual nodes improve load balancing. These are the core ideas behind modern distributed cache systems used by companies like Amazon, Netflix, and Uber. Every system we use today is built on a few fundamental concepts. Master those concepts and system design becomes much easier. If this video helped you, consider subscribing for more deep dives. Thanks for watching, and I'll see you in the next one.